In this video, you will learn about Newton's third law. You may have heard Newton's third law described as every action has an equal and opposite reaction. But what does that mean? Well, very simply put, it means forces come in pairs. Let's look at this example. Imagine we have a box, and there's a person who's pushing the box. We know the box will experience the force of the person pushing on it. But what Newton's third law says is that the person will experience the force of the box pushing back on them. And you've heard of this before. This is just like the normal force. Remember, I told you the normal force occurs when you have an object pushing down on a surface, and then the surface pushes back up on it. And if we wanted to describe the relationship between these two forces, we could use this equation, which says that the force of the person pushing on the box is equal to the negative of the force of the box pushing on the person. And so all this is saying is the force of the person pushing on the box has the same magnitude as the force of the box pushing on the person, but they are in opposite directions. And so that's what Newton's third law means. If there is a force acting on an object, the object will apply a force right back at it that has an equal magnitude but is in the opposite direction. And now you may have seen this more generically written as the force A on B is equal to negative the force B on A. And what this means is that if you have some object A that applies a force to object B, then object B will apply a force back on object A, and this force will be in the opposite direction. Now let's do a question to practice what we learned. So in this question, we have a 1 kilogram box and a 2 kilogram box that are right beside each other on a frictionless table. We are told that a 20 Newton force is applied to the 1 kilogram box. And based on that, what force does the 2 kilogram box apply to the 1 kilogram box? Now, if you're feeling confused as to where to start, always start with your free body diagrams. So I will draw 2 free body diagrams, one for the 1 kilogram box and the other for the 2 kilogram box. Starting with the 1 kilogram box, we know that there's a force that's pushing it with 20 newtons, and we also know that the 1 kilogram box will be pushing on the 2 kilogram box. And according to Newton's third law, that means that the 2 kilogram box will push back on the 1 kilogram box. So we also have to include the force of 2 on 1. And then of course there's the force of gravity and the normal force. Now let's look at the 2 kilogram box. Well, we know the 1 kilogram box is going to be pushing on the 2 kilogram box. We have to draw the force of 1 on 2. The other forces would just be the force of gravity and the normal force. And now it's really important that you recognize that the force of 1 on 2 is equal to the force of 2 on 1. They have equal magnitude, but opposite directions. Now the next thing you want to do is write your F net equations. I will start with the 1 kilogram box. We will have F net x, which will be the sum of all the forces acting along the x-axis, is equal to the 20 Newton pushing force minus the force of 2 on 1. The force of 2 on 1 is negative because it's a vector that points to the left. Now because these two boxes are moving, we can replace F net x with ma. Now let's work on the F net equation for the 2 kilogram box. Here we will have F net x is equal to force 1 on 2. And we can replace F net x with ma. Now looking at these equations, your next question should be, what is the acceleration? And it's really important that you recognize that the acceleration for the 1 kilogram box and the 2 kilogram box will be the same because the two boxes are connected and they move together. And now since they move together, we can actually consider them as a whole. So why don't I draw a free body diagram considering the two boxes as one object? And then we can see we have the 20 Newton applied force and the force of gravity and the normal force. And if we make an F net equation, we would just see that F net is equal to 20 newtons. We can replace F net with ma and rearrange and solve for the acceleration of the two combined objects. And the key here is that when you're inputting the value for the mass, you use the combined mass, which would be 1 kilogram plus 2 kilograms. And what we find is that their combined acceleration is 6.7 meters per second squared. So the two blocks are accelerating together at a rate of 6.7 meters per second squared. And now that we have the acceleration, we're ready to solve. And now we were asked to solve for the force of the 2 kilogram box on the 1 kilogram box. But we know, based on Newton's law, that the force of 2 on 1 is equal to the negative of the force of 1 on 2. So they have the same magnitude, which means we can solve for the force of 1 on 2 or the force of 2 on 1. We'll get the same answer. We might just have to change the sign. So for simplicity's sake, I'm going to solve for the force of 1 on 2. All I have to do is plug in the mass of the 2 kilogram object times the acceleration, and we see that the force of 1 on 2 is equal to 13 newtons. And based on Newton's third law, we know that the force of 2 on 1 is equal to negative 13 newtons. It has equal magnitude, but opposite direction. And so that's how you use Newton's third law to answer forces questions. Now the next thing we want to look at is a special use case of Newton's third law. And this comes up all the time in forces questions. And that's objects that are connected by ropes. So you can imagine if you have a tow truck that's pulling a car, or you have two masses that are connected by a pulley and ropes. Looking at our first example, based on Newton's third law, we know the force of the truck on the car is going to be equal to the force of the car on the truck. Looking at our second example, we know that the force of the second mass on the first mass is going to be equal to the force of the first mass on the second mass. That's just what we learned in Newton's third law. So why am I bringing this up as a separate topic? Well, it's because if we're dealing with two objects that are connected by ropes and they are accelerating, their acceleration is going to be the same because the objects are moving together. So if we look at our first example, the acceleration of the car is going to equal to the acceleration of the truck. It has to because they're connected and they're moving together. Now let's look at our second example. And these pulley questions come up all the time. So it's really important that you recognize that the acceleration of the first object is going to be equal to the acceleration of the second object, but they're going to be in opposite directions. And that's why this equation says A1 is equal to negative A2. And that makes sense because the first object is accelerating up and the second object is accelerating down. Now let's do an example to practice this. In this question, we have a 15 kilogram block and a 10 kilogram block, which are both hanging on opposite sides of a pulley. And we are asked to determine the acceleration of the blocks when they are released. So you can imagine the 10 kilogram block, which I'll label A, will accelerate up because the heavier 15 kilogram block, which I labeled B, will be moving down, which will pull it up. The first thing you want to do is draw your free body diagrams. So we will have to do one for the block A and another for the block B. For block A, we know there's going to be the force of gravity pushing down on it. And then because it's connected to block B, there's going to be the force of B pulling on A. And now if we look at block B, force of gravity pushing down on it. But because it's connected to block A, there's also the force of A on B. And you need to remember from Newton's third law that the force of B on A is equal to the force of A on B. Now the next thing you want to do is write your F net equations. Let's start with block A. We would have F net is equal to the force of B on A minus the force of gravity. We can replace F net with MA, and we can replace the force of gravity with mg. Now let's look at block B. We would have F net is equal to the force of A on B minus the force of gravity. We can replace F net with MA, and of course the force of gravity with mg. Now I'm going to go back up to block A, and I'm going to rearrange this equation to isolate for the force of B on A. Now the reason I did this is because based on Newton's third law, the force of B on A is equal to the force of A on B. That means I can take what I rearranged for the force of B on A and plug it into my force of A on B. And when I do that, I get this equation. And if you look at this equation, we have the mass of B, we have the mass of A, we have the acceleration due to gravity. All we need is the acceleration of the object B and the acceleration of the object A. And this is where it becomes critical that you recognize that the acceleration of A is just equal to negative the acceleration of B. They have the same magnitude but opposite directions. So what we can do is we can replace the acceleration of A with negative the acceleration of B. So I replace the acceleration of A with the acceleration of B, but don't forget the negative sign. And then all I have to do is rearrange and isolate for the acceleration of B. And once I've isolated for AB, I'm ready to just plug in my values. So I will plug in my values for the mass of A, the mass of B, and the acceleration due to gravity. And what we find is that AB, the acceleration for the object B, is equal to negative 1.96 meters per second squared. It's negative because object B was accelerating down. Now we also need to find the acceleration for object A, but that's easy because the acceleration for A is just equal to negative the acceleration for B. So object A is accelerating at positive 1.96 meters per second squared, which makes sense because it's accelerating up. And so that's how you use Newton's third law to answer questions about objects that are connected by ropes. And I urge you to practice these pulley questions because they come up all the time in the forces unit. And so let's just do a quick summary before we end. We learned that Newton's third law says that forces come in pairs, meaning if we have an object A acting on an object B, the object B will exert a force of equal magnitude but opposite direction on object A. And we can describe that with this equation. Then we also learn for objects that are connected, because they're moving together, their accelerations are going to have the same magnitude, but they may have opposite directions. And we saw that for our pulley question, where the acceleration of object A was equal to negative the acceleration of object B. They had the same magnitude, but opposite directions. And that's the end of this lesson on Newton's third law.